All right. Hello, everyone. Today is April 10th, Saturday. It's Saturday morning. I stopped by the community center of my apartment to take lecture videos. Um, hope you guys had a great week and enjoy the weather, nice weather during the week, and stay healthy and doing well. So I'm first of all, I have to say I'm sorry, really sorry about the late uploading this video. As I wrote down in the course website, um, it took me almost 2 days in full understanding, digesting material in Musgrave Winston Green. And so the main problem is I've taught general equilibrium theory before at graduate school, but at that time I just taught very basic stuffs like a first welfare theorem or second welfare theorem, or how to compute part efficient allocation in a simple model. This week I'm going to illustrate uniqueness and stability and the core, some advanced topics, but I never ever presented that kind of advanced topics in class. So I needed some time for my presentation. So I had to think about how to present these advanced topics in class, and also had to think about so what I learned in my graduate school, when I sorted out some topics from Musgrave Winston Green, because there are many topics in Musgrave Winston Green about the general equilibrium. So I had to some sort of some important topics on the basis of my past experience in graduate school. So I had to look back into my graduate school and to think about what I learned in that school. So it also took me some time. Uh, so that's why I was a little bit late. Okay, hope you understand this. And furthermore, today I have a little bit sore throat right now. So I can speak loudly and clearly. But as soon as but I will do my best taking this lecture video, some lecture videos today, and as soon as my voice is back, I'm gonna keep recording other videos. Okay, so we'll try to upload the lecture videos as soon as possible. All right. So let me first illustrate where we are. So far we studied several topics about general equilibrium in positive theory and in normative theory. As for positive theory, we studied the existence issue last week. So in the last week, I showed you how to prove the existence of equilibrium using Brouwer's fixed point theorem. So for that purpose, we first narrow down the scope of model to pure exchange, and we made a couple of assumptions on the primitives, especially on the consumer's preference relation. So we assumed strict convexity and strong monotonicity. Okay, and particularly strict monotonicity is quite important because under that assumption, we know that excess demand is going to be a function, not a correspondence. Okay, so Brouwer's fixed point theorem is for fixed point in case of function. Okay, so we didn't have to use other advanced fixed point theorem to prove the existence of Walrasian equilibrium. Okay, under the assumption of strict convexity. So the way to deal with existence in Musgrave Winston Green is quite general. So they allow for a general framework, and they worked with excess demand correspondence, and they adopted a Kakutanis fixed point theorem. As I told you, if you studied advanced game theory, you may have seen the way to prove the Nash equilibrium. In John Nash's original proof, he adopted Kakutanis fixed point theorem. That is for fixed point in case of correspondence. That's how the Musgrave Winston Green treated the existence issue in the book. Okay? But we took a little bit slightly different approach and way simpler approach by narrowing down the scope of the model and by making some assumptions on the primitives. Okay, but the existence sounds very tedious, but very important issue. So it is instructive to see that how to prove existence in economic model line by line. So that's how we did, and that is also why we studied existence together last week, right? And in positive theory, we are left with two topics: uniqueness and stability. Okay, so we are going to so in this video, I'm going to talk about uniqueness. And as for normative theory, we studied two welfare properties of equilibrium. First, the welfare theorem, and second. We also discussed Pareto efficiency and the relationship between Pareto efficiency and social welfare maximization problem. And the one remaining topic in this normative theory is the relationship between equilibrium and the core. So core is another solution concept that predicates upon the cooperative game theory. And I think I can introduce this concept in the last video of this week. So to summarize, we are left with three topics in general equilibrium: uniqueness, stability, and the relation between core and equilibrium. So I'm going to address these three topics this week. And next week, we are going to deal with some applications. And in the week after next, so finally we finish the first part of this course, general equilibrium, and then we finally move on to mechanism design theory. Okay, so that is my current plan. All right, so as I told you in this video, I'm going to talk about uniqueness. So let me first introduce that topic. So uniqueness is quite useful and is important topics as much as the existence of equilibrium. So if we know our equilibrium is unique, okay? Also our prediction is unique, then of course it reinforces the predictive power. Okay? So that's quite useful. If we know equilibria are multiple, so that means we predict this situation may happen or the other situation may happen. Okay, and in that case, our prediction is more like ambiguous. So we don't know what situation happens in the end. Okay, so that of course undermines the predictive power. But if we know the equilibrium is unique, then we can make a clear and accurate and unambiguous prediction about people's behavior. So that is quite useful. Okay? And furthermore, in general equilibrium context, it is quite useful. Uniqueness is quite useful whenever we calculate the necessary redistribution of wealth for achievement of Pareto efficiency. In order to explain this, let me go back to the second welfare theorem. So according to the second welfare theorem, we know that any Pareto efficient allocation can be achieved by market mechanism after redistribution of wealth. So going back to this slide, we have initial endowment. So initial endowment point is given by this, okay? And suppose the central authority wants to achieve this allocation as an equilibrium using market mechanism, okay? So in the current situation, consumer 1 has a larger income than necessary, especially necessary for achieving this allocation as an equilibrium. So central authority has to start by redistributing wealth transferring money from consumer 1 to consumer 2. Okay? So that will shift down. So that will shift this budget line of consumer one down to this one. Okay. So the amount of wealth transfer to achieve this allocation as an equilibrium is captured by the gap between these two lines. All right. But suppose that we have a multiple equilibria supporting this x star as an equilibrium. So this one can be an equilibrium vector, or this one is also equilibrium vector. Okay? Now you can easily see that depending on the choice of equilibrium price vector in case of multiple equilibria, the necessary amount of redistribution of wealth will be different. Okay, so if we adopt this one, then we need this amount of wealth transfer. Okay, but in case of this one, okay, then actually the consumer 2 has to transfer money to consumer 1, because now this omega is below this price vector line. Okay? So depending on the choice of equilibrium, in case of multiple equilibria, we have a different redistribution of wealth. Okay? So that weakens the validity of the second welfare theorem. So we have to rethink about how much redistribution of wealth is necessary for achievement of parity efficient allocation. So it does not validate the second welfare theorem. Okay. So in that sense, uniqueness of equilibrium is quite useful for the second welfare theorem. Right. So we are going to study two conditions under which Walrasian equilibrium is unique. The weak axiom of limited preference. So we are going to study two conditions. In Musgrave-Winston-Green, there are actually 4 conditions. So we are going to study 2 of them. The first condition is the weak axiom of limited preference. So we've seen this axiom when we proved the first welfare theorem, and then it turns out that this simple axiom, so this condition, also plays a pivotal role in improving the uniqueness of equilibrium. Okay, and we are going to see why. And the second property is called the gross substitute property. If you studied intermediate microeconomics, I guess you've heard about gross substitutes. So that this property comes from the standard definition of gross substitutes. Is a pretty natural extension of the concept of gross substitutes. And yeah, under this property as well, so under this condition as well, we can show that Walrasian equilibrium is also unique. Okay, so we are going to study that too. And throughout the analysis, we maintain the assumption that strict preference relation is strictly convex and strongly monotone. So if we go back to previous week lecture slide, if a preference relation is strictly convex and locally non-satiated, that was actually a typo. It is a strongly monotone. So if the preference relation is a strictly convex and strongly monotone, we know that aggregate excess demand function possesses these 4 properties: continuity and homogeneous of degree 0 and Wallace law, and bounded from below and above. Okay. So by assuming preference relation is strictly convex and strongly monotone, we know that excess demand function has these 4 properties. So we maintain these 2 assumptions. So meaning that we assume every consumer's utility function is strictly quasi-concave and strictly increasing. Okay? So that we can work with excess demand function with these four properties. All right. So let me first reintroduce the weak axiom of liberty preference. So the idea is really simple behind this. So the axiom says that under price vector P, I'm going to choose a bundle XOP. Okay? And then there is another bundle, X of P prime. Okay? This is what I'm going to choose under price vector P prime. Okay? So I have two alternatives. One bundle XOP and another bundle XOP prime. But under price vector P, I'm going to choose XOP. Although here P dot XOP is a total expenditure necessary for choosing XOP. Okay, so this is a kind of money in my pocket. So I have this amount of money. So XOP is affordable. Okay, and the right side P dot XOP prime is a total expenditure necessary for this bundle. So we have this inequality, meaning that I could have chosen bundle XOP prime, with my budget. With my current budget, these two bundles are affordable. But nevertheless, I choose XOP. That means, I strictly prefer XOP to XOP prime. Okay? So that is my consumption behavior under price vector P. Now suppose that price vector changes from P to P prime. Okay? Under this price vector, I'm going to choose XOP prime, okay, rather than XOP. Okay? And then to be consistent, under price vector P prime, my preferred bundle XOP should not be affordable. So that must be outside of my budget set. In other words, the total expenditure for XOP under P prime should exceed my current budget. Right? So that is a implication. It's a very reasonable and weak assumption about people's behavior. Okay? That is a weak axiom of liberty preference. So in order to better understand the concept, I prepared two examples. So in one of which weak axiom is satisfied, and in the other, the axiom is not satisfied. Okay, so let's think about the figure on the left. Okay, so it's not that clear. So let me first clarify the price vector. So this one is a under budget set under P prime, and this one is under P double prime. Okay, price vector P double prime. All right, so this budget line is going to be the budget line under P prime, and this line is the budget line under P double prime. Okay, so now under P double prime, okay, I'm gonna choose this yellow bundle. Okay, but under P prime, I'm gonna choose this green bundle. Okay, so the situation is like this. Under P double prime, I could have chosen green one and yellow one, but instead of green one, I choose yellow one, meaning that I strictly prefer XOP double prime. Okay, this yellow bundle to green bundle. Okay, so when price vector changes to P prime, okay, now I'm going to choose the green one instead of yellow one. Okay, and for my behavior to be consistent, okay, so for kind of consistency about my consumption behavior, under price vector P prime, now yellow bundle is not affordable, should not be affordable. So now yellow bundle in this figure is outside of this triangle, my budget set under price vector P prime. Okay, so that is consistent with the weak axiom of limited preference. And here is one more example. So once again, to clarify the budget set, this is the budget set under P double prime, and this one is under P prime. Okay, so under price vector P prime, okay, I'm gonna choose this green bundle, but under price vector P double prime, I'm gonna choose this yellow bundle. Okay, so the situation is like under price vector P prime, both green and yellow ones are affordable. Okay, but nevertheless, I choose this green bundle. So I strictly prefer this green one to yellow one. Okay, but if the price vector changes from to P double prime, so now this is my budget set. Still, these two bundles are in my budget set. So I could have chosen one of these two bundles, but I choose this time yellow one. Okay, that is inconsistent with my previous consumption behavior under P prime. So that violates the weak axiom of limited preference. All right, so I think this is clear. So now let me go to now let me discuss how to extend this standard weak axiom into the case of excess demand function. So remember, excess demand function is a primary mathematical tool for equilibrium analysis. Okay, and the extension is quite natural. It's pretty easy. Now, let me take one note here. Okay, so we have this axiom, all right? So P dot X of P is larger than P dot X of P prime. Oh, let me make some room between these two. So P dot X of P prime. Okay, so from this inequality, let me subtract away P dot omega from both sides. Okay, then the left side becomes P dot X of P minus omega. So omega is this omega is an initial endowment. Right? So I can factor out P, and similarly I can factor out P from the right side. Then we'll be left with X of P prime minus omega. Okay. So the expression in the parentheses now, this is excess demand function at price vector P, and this is excess demand function at price vector P prime. Okay, but by Waller's law, P dot Z of P is equal to 0. We know that this is equal to 0. So by Waller's law, this is a 0, and the right side is P dot Z of P prime. Okay, so the first inequality, this inequality translates into this one. Okay, so that is why we have this. P dot Z of P prime is lower than or equal to 0. Okay, and we have one more condition. Z of P should not be equal to Z of P prime. Okay, so now we compare the two price vectors P and P prime, right? Because remember, Z function is homogeneity of degree 0. So Z is homogeneous of degree 0. Okay? Meaning that z of p is equal to z of alpha p for every constant alpha, every positive constant alpha. Then, we have a homogeneity of degree 0. So if p is a proportional to alpha, if p is linearly proportional to p prime, so if we have some constant alpha between these two price vectors, so these two vectors are linearly dependent, okay? Not independent, but dependent. Okay? Then we know these two, so z of p and z of p prime they are equal to each other. Okay, so in such a case, we have some problem, so we needed this condition. Okay, so that ensures that p is not linearly proportional to p prime. Okay, so we compare two linearly independent price vectors. Okay, and the right side. Okay, so these two imply. So the right side now, by subtracting away p prime dot omega and p prime dot omega from both sides, you can easily see that the left side becomes p prime dot z of p, and the right side becomes p prime dot z of p prime. So by Waller's law again, that is going to be 0. So we have this inequality. All right. So this is weak axiom of limited preference in case of excess demand function is a natural extension of a standard weak axiom. Okay. So the weak axiom says p is revealed preferred to p prime. So then p prime cannot be revealed preferred to p. Okay. So the interpretation is under price vector p, we could have chosen two excess demand functions, z of p prime and z of p, both one. Okay, so p is revealed preferred to p prime, but in price vector p prime, z of p, it turns out that z of p is larger than 0. Dot product is larger than 0, meaning that z of p is infeasible. Okay, so p prime cannot be revealed preferred to p. And its geometric interpretation is right here. That is captured by this figure. So under price vector p, we can choose z of p, right? Under price vector p, actually both excess demand functions are feasible because they are under in this region, right? So the dot product p between p and z of p prime and z of p are less than 0. Okay? Less than 0. But under price vector p prime, still, these two excess demand functions are feasible. These two excess demands are feasible. So that this is a violation of the weak axiom. Okay? Once again, under price vector p, excess demand is z of p, although z of p prime is feasible, meaning that this is revealed preferred to z of p prime. But now under price vector p prime, still two excess demands are feasible. But in this case, excess demand is not this one, not z of p, but z of p prime. Okay. So the another angle to see this, okay, and think about the geometric interpretation of the dot product. If the dot product yields some negative value, that means the angle between these two vectors is obtuse, is higher than 90 degrees. So here we have price vector p, and the z of p prime is right here. If we interpret that as a vector, So with this origin, price vector P is right here, and Z of P prime is right here. So the angle formed by these two vectors is obtuse, meaning that higher than 90 degrees, right? So P dot Z of P prime is a negative value. Then, to satisfy the weak axiom, P prime dot Z of P must be positive. The positive sign of the dot product, meaning that the angle between these two vectors is now acute, so less than 90 degrees. Okay? But in this example, Z of P is right here. Okay? And the P prime is given by this vector. So this vector. Okay? So the angle between these two vectors still obtuse. So that is a violation of this weak axiom. So in order to satisfy the weak axiom, Z of P must be, so Z of P must be here. So on this piece of line segment, okay, below this the origin, or above this origin, okay, in this case, P dot, P prime. So the angle between P prime and Z of P is now acute. Okay, so that means P dot Z of P is now larger than 0. Okay, so that is consistent with a weak axiom. The intuition is, if Z of P, excess demand under price vector P, if that was at this point rather than this point, right? So now under price vector P, Z of P and Z of P prime both are feasible, okay? But the excess demand is right here. Okay? That means Z of P is revealed preferred to Z of P prime. And under P prime, if the excess demand is right here, that means Z of P is now the outside of a feasible set. Okay, so that is consistent with the weak axiom. All right. So the last bullet point tells us. So this weak axiom sounds like a very weak condition. So it turns out that it is always satisfied for single individual behavior. So if we predict about single person's behavior, consumption behavior, and then this weak axiom is always satisfied as long as this individual is a rational. If this individual preference relation is complete and transitive, okay, as long as the preference relation satisfy these two axioms, completeness and transitivity, we can make sure that this consumer's behavior satisfies the weak axiom. But it's going to be a strong condition about aggregate excess demand function Z. Okay, we make assumption, weak axiom assumption work on the aggregate excess demand function. Okay, to see why this is a strong condition. Actually, that appears in chapter 4.c in Musgrave, Winston Green. So let's consider this example. Okay, so here we have two price vectors, P and P prime. Okay, and under price vector P, consumer 1, okay, consumer 1 choose this one. Okay, and under price vector P prime, consumer 1 choose this one. Okay, now you can easily see that consumer 1's behavior consistent with weak axiom, and consumer 2, by the way, under price vector P, choose this one, but under price vector P prime, consumer 2 chooses this one. Okay, so also consistent with weak axiom. Okay, but if we now examine the aggregate demand, whether aggregate demand satisfies the weak axiom. Okay, so now under price vector P, so under P, if we now examine the aggregate demand, so x1 plus x2, so x1p plus x2 of p. Okay, and then in order to express the aggregate demand in the same figure, let me divide it by 2. Okay, so that's going to be average aggregate demand. So that point is right here, this point. Okay, and under price factor P prime, the average aggregate demand is right here. Okay, so if we now compare these two, all right, then that is inconsistent with weak axiom, because under price vector P prime, two bundles are affordable. Okay, so now aggregate consumption behavior is inconsistent with the weak axiom, because under price vector P prime, both are affordable. Okay, but which are the consumers choose this bundle, right? But under price vector P, still affordable, both are affordable, but consumers choose different bundles. So this figure demonstrates that so although weak axiom satisfied for every consumer, is not necessarily satisfied for aggregate behavior. Okay? So for aggregate excess demand function, verb becomes a strong condition. Okay. Nevertheless, for our purpose, and we are going to show that this verb is going to be is going to guarantee the uniqueness of equilibrium. So we are going to show that if aggregate demand function satisfies the verb, then the set of Walrasian equilibria is convex. Okay, and the Walrasian equilibrium under strong monotonicity. So originally, with a local non-satiation, equilibrium condition was this. But under strong monotonicity, it becomes this. So the Walrasian equilibrium will be characterized by this equation. This is what we studied last week. So the set of Walrasian equilibrium price factors is going to be price factors such that z of p is equal to 0. Okay, but we are going to show that if z satisfies the verb, this set is convex. That means if the set of equilibria is a finite, so if there are only finite set of numbers, so finite number of price vectors satisfying z of p equal to 0, and it can be at most one equilibrium, because convex set means so convex set looks like this. If we have two price vectors p1, p2, are in this set, if this set is a convex, every line segment connecting these two price vectors also lies in the set. Okay, but in case of finite set, we have just some several distinct points. Then there is no possibility these finite distinct points can be a convex set, because now the line segment connecting any points any between any 2 points among these, does not lie in the set. So if the set of equilibria is finite, only single point, only this set is a convex. The set with a multiple distinct points cannot be a convex set. So with that in mind, so if we show that the set of equilibrium is convex, then if the set of equilibrium is a finite, then we can show the existence of uniqueness of equilibrium. And then the set of equilibrium, so we are going to show only this fact, but in almost every case, we can show that the set of equilibria is a finite. We can't have infinite number of equilibrium. Okay, so if we show that this is a convex, then we establish the uniqueness of equilibrium. Okay? All right, so the way to prove this statement is we are gonna adopt a proof by contradiction. So we first negate the conclusion. So suppose to the contrary that this set, the set of Walrasian equilibria is convex. So we have a two price vectors, z of p so we first negate the conclusion. So the set of Walrasian equilibria is not convex, meaning that we have here two price vectors p and p prime. These two price vectors are in the set. Okay, they are elements of this set, but they're linear combination. So alpha p plus 1 minus alpha p prime, their linear combination for some alpha does not belong to the set. Okay, that means excess demand function takes a non-zero value at this price vector as some linear combination between these two. Okay, then what do we have? What can we infer from the verb weak axiom? So by the verb, it follows that p double prime dot z of p, because we assume that p and p prime are equilibrium price vectors. So are elements of this set. So z of p and z of p prime are equal to 0. That is that, these two are zero vectors. So for such a zero vector, dot product should be equal to 0. Okay, so by the weak axiom, we must have, if we interchange these two price vectors, we must have a positive value. Okay, and similarly, if we have, so if we compare p double prime dot z of p prime, if we consider the dot product between these two, that is also equal to 0 because we know z of p prime is equal to 0. Okay, and that implies, so the verb implies that p prime dot z of p prime is strictly positive. All right, then let me multiply. So let me multiply the first inequality by alpha and the second inequality 1 minus alpha. Okay, and if we add these two inequalities, then we have on the left hand side alpha p dot z of p double prime plus 1 minus alpha p dot p prime dot z of double p prime. Okay, and the right side is just this. Right side is just a 0. The right side of the inequality is still 0. And if we think about the left hand side, this expression boils down to z p double prime dot product alpha p plus 1 minus alpha p prime. Okay, but this is a p double prime. Okay, so the work gives us another inequality that says p double prime dot zl p double prime. That is strictly positive, but it contradicts with the Wallace law. By Wallace law, dot product between these two should be equal to 0 because the price vector and the excess demand function at the same price vector should be equal to 0 by Wallace law. Alright, so we started by negating the conclusion, and then we obtain some contradiction. So that means the contrapositive of the statement of this, the contrapositive statement of this one is always true.